Welcome to Orbit Observer. It's lovely to have you here tonight. Wherever you are right now, however the day has treated you, you've arrived somewhere quiet. Maybe you're tucked under a blanket with the lamp still glowing soft and low across the room. Maybe you're lying flat with your eyes already half closed, the phone propped somewhere it can keep talking long after you've drifted off. Maybe you're on a train, or a couch, or a long dark drive, and the world outside is sliding past in the kind of hush that only comes late. Wherever you are, settle in. You don't have to do anything now except breathe slow and let the night gather around you. Before we begin, just one small thing gently. If you enjoy these slow journeys through the sky, and you'd like more nights like this one, a quiet like and a subscribe really does help this little channel keep going. Small creators like me genuinely rely on it, and I'm grateful for every single one of you who taps that button in the dark, and to those of you who've already subscribed, who come back night after night and let me keep you company while you fall asleep. Thank you, truly.
You're the reason I get to do this, so tell me, before your eyes get too heavy, where in the world are you watching from tonight? What time is it in your corner of the world? Leave it down below if you like. I always love to imagine the map of you, scattered all across the planet, all drifting off together under the same dark sky.
Now, a soft warning, the kind I always give. I'll do my best not to make tonight so interesting that it keeps you awake. But if it does, well, at least you'll have learned something lovely along the way. A fair trade, I think, and honestly, there's no pressure to follow every word. None at all. You can let the facts wash over you like warm water. If you drift off before the end, that's perfectly fine. The moon we're visiting tonight has been doing what it does for a very, very long time, and it'll still be doing it in the morning. The ideas will keep. They'll be here when you wake. So, you don't have to hold on tight. You don't have to remember any of it. Just let it carry you. Because tonight, we're going somewhere small. Somewhere far. Somewhere almost no one ever thinks about when they look up at the night sky. We're going to a tiny moon, way out past the asteroids, way out past Jupiter, all the way to the ringed planet Saturn. And we're going to spend this whole slow night with just one of its moons, one little world. We won't rush off anywhere else. We won't dart from planet to planet or pile on 100 different places. Just this one, soft and patient. Fact by gentle fact, its name is Enceladus. It's a strange and beautiful little name, isn't it? Enceladus. It rolls around in the mouth like a pebble. We'll get to where that name came from later, much later, deep in the quiet of the night. For now, just hold the sound of it. Enceladus. A tiny moon of Saturn wrapped in ice, hiding something extraordinary. Let me start with the picture that first made scientists fall in love with this place. Because here's the thing about Enceladus. It's small, really small. When you imagine a moon, you might picture something enormous, something that hangs heavy in the sky, the way our own moon does over a quiet field at night. But Enceladus isn't like that. It's only about 500 kilometres across. That's a little over 300 miles from one side to the other. And I know that's still a big number to say out loud, but think about it this way for a moment, slowly, the way you might trace a shape with your finger on a foggy window. 500 kilometres. You could take this entire moon, this whole frozen world, and you could set it down inside a single state of the United States, and it would fit. You could nestle Enceladus snugly inside the borders of Arizona, with room to spare around the edges. The whole moon, the mountains of it, the plains of it, the ice of it, the hidden depths of it, all of it, tucked into one corner of one country on one planet. It's a moon you could hold in the cup of a map.
A whole world small enough to hide in a single state. And that's the part that makes what comes next so quietly astonishing, because this tiny thing, this little ball of ice you could tuck into Arizona, is doing something that almost nothing else in the entire solar system does. It's firing fountains of water into space.
Let that settle for a second. Fountains of water, real water, geysers rising up off the surface of a frozen moon, blasting out into the black and the cold and the silence, hundreds upon hundreds of kilometres high. Not steam from a kettle, not a wisp. Great soft plumes of water vapour and tiny grains of ice jetting continuously up off the south pole of this little world and out into the dark. A moon small enough to fit inside Arizona, quietly firing fountains of seawater into space, and it's been doing it, as far as we can tell, for a very long time. It didn't pause for our cameras, it didn't put on a show, it's just there, in the deep cold, breathing water into the night, the way it always has. We'll come back to those fountains, we'll spend a good while with them because they're the heart of why this moon matters so much. But for now, just hold that image as you lie there. A tiny, bright moon, far out by Saturn, with silent, ghostly plumes of water rising off it like breath on a winter morning, like a sleeping thing exhaling slowly into the cold. Now let me tell you the next thing about Enceladus, and this one is the calmest, gentlest fact of all, the kind that asks nothing of you. It is, as far as we know, the whitest world in the entire solar system. The brightest, the most reflective, the cleanest. Of all the planets and moons and rocks we've ever looked at out there, nothing shines back at us quite like Enceladus does. Its surface is almost pure, fresh, clean ice, and it reflects something like 90% of all the sunlight that ever touches it. 90%. Almost all of it bounced straight back out into space. Think of fresh snow on a still morning, the kind that's fallen overnight and lies untouched, so blindingly bright in the early sun that you have to squint. Enceladus is brighter than that. It's a polished snowball hanging out there in the black. Scientists have a word for how reflective a surface is. They call it albedo, which is really just a measure of how much light a thing throws back instead of soaking up. A lump of dark coal has a very low albedo. It drinks the light in. Fresh snow has a high one. And Enceladus has just about the highest albedo we've ever measured anywhere, sitting up near the very top of the scale, close to a perfect mirror. A world like a pearl. A little ball of clean ice, polished smooth, gleaming in the dark. And here's the quiet, beautiful consequence of all that brightness. Because Enceladus throws back almost all the sunlight that reaches it, it barely absorbs any warmth from the sun at all. The light just bounces off and leaves, so the surface stays brutally, deeply, profoundly cold. We're talking about a temperature down around minus 198 degrees Celsius. That's roughly minus 330 degrees Fahrenheit. Numbers so far below freezing they almost stop meaning anything. So cold that the ice there isn't soft and slushy like the snow you might scrape off a windscreen. At those temperatures, water ice becomes hard, hard as stone. You could carve it, build with it, walk across it like rock. The whole surface is a frozen shell, harder than any winter you've ever felt, gleaming white and still in the dark, so far from the sun that the sun out there is little more than a very bright star. A polished snowball, mirror bright, colder than anything you've ever touched, hanging silently in the black beside a ringed planet. And yet, somehow, breathing water into space. Hold those two things together for a moment. The cold and the fountains. The frozen still surface and the living jetting plumes. It almost doesn't make sense, does it? How can something that cold be doing something that active? We'll get there. We'll unfold it slowly. There's no rush at all. Let me take you down now, gently, to the place where those fountains come from, to the south pole of this little moon, because the geysers don't come up from just anywhere. They don't dribble out all over the surface in 1,000 random places. They rise from 4 particular cracks, 4 long fractures in the ice, all of them gathered near the moon's south pole, lying roughly parallel to one another, like the marks of some enormous, gentle claw drawn across the white. When the scientists on the Cassini mission first saw these cracks in their images, they noticed something about them. The ice around these fractures looked different. It was warmer and faintly coloured, marked in a way the rest of the bright surface wasn't. And because the 4 cracks ran side by side, in those long parallel lines, somebody looked at them and thought of the stripes on a tiger. And the name stuck, the way good nicknames always do. The tiger stripes. That's what everyone calls them now, even the scientists. The tiger stripes of Enceladus. 4 warm, glowing fractures near the South Pole, where the moon breathes water into the sky. But the tiger stripes are only their nickname. Each of those 4 cracks has a formal name too, a proper name, and this is where the story turns lovely and a little dreamlike, because the people who name the features of this moon decided to draw on the world of the Arabian Nights, those old tales of 1,001 nights of stories told in the dark to hold off the dawn. And so each of the 4 cracks at the south pole of Enceladus carries the name of a city out of those tales. There is Alexandria, there is Cairo, there is Baghdad, and there is Damascus, 4 cities of story and spice and lamplight, their names now drawn across the south pole of a frozen moon 1 billion kilometres from any of them. The scientists call them Sulci, which is just the formal word for these long grooves and furrows in the ice. So properly, they are Alexandria Sulci, Cairo Sulci, Baghdad Sulci, and Damascus Sulci, but you don't need to hold the formal word, just hold the picture. 4 glowing cracks near the south pole of a tiny ice moon, each one named for a city out of the Arabian Nights, and out of those 4 cracks, slowly and silently, water rising into the dark. Stories told in the night, breathing out into the night. There's a kind of poetry in that the universe didn't have to give us, and yet here it is. So now you have the surface of this place, a small, bright, frozen world, white as a pearl, hard as stone, terribly cold, with 4 warm cracks near its south pole, named for old desert cities, gently fountaining water out into space. And already that would be a marvel. Already that would be enough for one little moon to be famous. But it isn't the real wonder. The real wonder is what's underneath. Because here is the question that the fountains forced everyone to ask. Where is all that water coming from? You can't fountain water you don't have. Those plumes have been running and running, hundreds of meters of water vapor and ice grains jetting up off the South Pole over and over for a very long time. And that water has to come from somewhere. It has to have a source, a reservoir, something feeding it from below, deep inside the moon. And as the scientists looked closer and measured more carefully and thought it through, they arrived at an answer so beautiful and so strange that it changed the way we think about this whole little world. And in truth, about how many places out there might be more interesting than they look. Beneath the ice of Enceladus, beneath that hard, frozen shell, there is an ocean. Not a puddle, not a buried lake hiding in one corner, a global ocean, a whole sea of liquid salt water wrapped entirely around the moon, sealed in beneath the ice like water held inside a shell. Imagine that for a moment, slowly, as you lie there in the dark. Picture this small, white, frozen ball. And now picture just below its surface, hidden from every eye, all the way around, in every direction, a complete and continuous ocean, dark and quiet and liquid and salty, sealed under a roof of ice. A whole sea on a moon, you could hide inside a single state. A sea no light has ever touched. A sea that has never seen a sky. When I first really understood that, it stopped me. The idea that out there, so far from the sun, on a tiny moon most people will never even hear the name of, there is an ocean. A real ocean with real water, salty like our own seas, sloshing slowly in the dark beneath miles of ice. And it raises 1,000 gentle questions, doesn't it? But the very first one, the one you might be asking right now as your eyes get heavy, is simple.
How on earth do we know? How can anyone possibly know there's an ocean inside a moon we've never drilled into, never landed on, never seen beneath the ice? We can't lift the lid. We can't peer down through the frozen shell. So how could anyone be sure? And the answer to that is one of the cleverest, quietest pieces of detective work in all of space science. So let me tell it to you slowly, because it's the kind of thing that's lovely to fall asleep on.
The scientists watched the moon turn. That's it, really, at the heart of it. They watched very, very carefully the way Enceladus rotates as it travels around Saturn. And they noticed something. They noticed a wobble. Now every spinning thing wobbles a little. Picture a spinning top as it slows, the way it doesn't just spin perfectly upright, but rocks and nods gently as it goes. Moons do something a little like that too, a slight rocking back and forth as they orbit. And the scientists have a word for it. They call it libration. It's just a small, regular wobble in the way a moon turns. And the thing about that wobble is that its exact size tells you something about what the moon is made of inside, about whether it's solid all the way through or whether something inside it is loose. Because here's the gentle bit of reasoning. If Enceladus were frozen solid all the way to its core, one single rigid lump of ice and rock, it would wobble in one particular way as it turned, a small, stiff wobble. But if there were a layer of liquid inside it, an ocean, separating the outer shell of ice from the rocky core beneath, then the outer shell wouldn't be locked tightly to the inside anymore. It would be floating just a little, free to slosh and shift on top of that hidden sea. And a shell that floats on a liquid wobbles more than a shell that's frozen solid through. It rocks a little further. It nods a little deeper. So the scientists measured the wobble. They watched the moon turn frame by careful frame, and they measured exactly how much Enceladus rocked as it went. And the wobble was too big, far too big for a moon that was frozen solid. The only way to explain a wobble that large was if the outer shell of ice was detached from the core beneath, floating on something liquid, riding on a global layer of water that let the whole frozen surface slosh ever so slightly as the moon turned. A wobble too big to be solid, that was the fingerprint, that was the quiet, beautiful proof. This was confirmed and laid out carefully by a team of scientists, the work of Thomas and his colleagues. Published in the journal Icarus back in 2016, they watched a moon nod in the dark, and from the size of that nod they knew with real confidence that there was a whole ocean hidden inside it. An ocean no one had ever seen, revealed by nothing more than the gentle rocking of a turning world. Isn't that a soft and lovely thing to think about? That you can know the inside of a thing by the way it moves. That a hidden sea, sealed under miles of ice, billions of kilometres away, can give itself away just by the way the moon it lives inside rocks ever so slightly as it spins. We never had to crack it open. The moon told us, in the only language it had, just by the way it turned. So now hold the whole picture, the one we've slowly built tonight, and let it rest in your mind as you drift. A tiny moon, small enough to nestle inside Arizona, white as a pearl, brighter than fresh snow, the most reflective world we know, so cold its ice is hard as stone, minus 198 degrees on the surface, lit by a sun that's no more than a very bright star. 4 warm cracks near its south pole, named Alexandria, Cairo, Baghdad, and Damascus, for cities out of the Arabian Nights. And out of those cracks, silent fountains of water rising into the black. And beneath it all, beneath the hard, bright shell, a hidden global ocean. A whole salty sea, sealed in the dark, wrapped around the moon, never touched by light, slowly rocking, slowly sloshing, as the little world turns and turns around its ringed planet far away.
That ocean is the heart of everything. Every wonder we'll uncover tonight comes back to that buried sea. The fountains come from it. The strange chemistry comes from it. The reason scientists can't stop thinking about this tiny moon, all of it comes from that one astonishing fact that under the ice of Enceladus there is water. Liquid water. A real ocean, warm enough to stay liquid in a place so cold the surface freezes harder than rock.
And that right there is the question that should be tugging at you gently as you start to sink toward sleep. Maybe it's already begun to. How? How can there be liquid water inside a frozen moon so far from the sun, in a place so brutally cold? Water should freeze out there. Everything freezes out there. The surface certainly has. So what keeps that ocean from freezing solid? What keeps a hidden sea liquid and warm in the coldest, darkest, loneliest place with almost no sunlight at all to warm it? There's an answer. A beautiful one, gentle as everything else about this moon. It has to do with squeezing and with rhythm and with a quiet tug of war between Enceladus and another moon entirely. The ocean isn't kept warm by the sun at all. It's kept warm by something far stranger and far more patient. But that's a story for a little further into the night, when you've sunk a little deeper, when the dark has settled a little further around you. For now, just rest with the wonder of it. A tiny bright moon far out beyond everything, with a whole ocean hidden in its heart. Breathing water into the dark, rocking softly as it turns, keeping its secret sea warm and liquid by some quiet magic we haven't gotten to yet. There's no need to stay awake for it. The ocean's been there a long, long time. It'll still be there when we get to it. It'll still be there in the morning. So let your thoughts go soft now. Let the picture blur a little at the edges, the way the whole world does just before sleep. A polished snowball far away in the dark, breathing slowly, keeping its warm sea safe under the ice. And we're only just beginning to understand it. There's so much more still, waiting in the quiet. Welcome to Orbit Observer. It's good to have you here, wherever you are tonight. Maybe you're under a heavy blanket with the lamp still on. Maybe you're on a couch or a train or somewhere far from home, and the day has finally let go of you. However you've arrived. You can stop holding anything now. There's nothing here to keep up with, nothing to remember, nothing you have to understand. I'll do the talking slowly, and you can just listen, or half listen, or drift right off in the middle of a sentence. That's all perfectly fine. The moon we're talking about has been doing what it does for a very long time, and it'll keep doing it whether either of us is awake to notice. And if you'd like more nights like this one, a gentle like and subscribe really does help this small channel keep going. To anyone already here with me, already part of this, thank you. It means more than you know. Small creators like me really do rely on it, and I'm grateful for every one of you. So tell me, before you sink too far down, where in the world are you listening from tonight? What time is it in your corner of the dark? I always like to imagine you out there, scattered across the planet, all settling in at once. Now, settle in. Let me give you the picture again, slowly, because it's worth holding in your mind as you fall. Picture a moon, not a big one, not a great cratered giant filling your sky. A small one, about 500 kilometres across. That's it. 310 miles end to end. Small enough that if you could lift it up and set it down gently on a map of Earth, It would tuck neatly inside the borders of a single American state. You could nestle the whole of it inside Arizona and it wouldn't quite reach the edges. A whole world, complete with everything it needs to be a world, and yet small enough to hide in one quiet corner of one country. And this little thing, this small bright pebble of a moon, is doing something almost impossible to believe. From cracks near its southern end, it is quietly firing fountains of seawater up into space. Real water, salt water, rising off the surface in slow, silent jets, drifting up and out into the black, where there is no air to slow them and no warmth to hold them. A tiny moon far out past the asteroids, past the great banded face of Jupiter, all the way out at Saturn, and it is breathing water into the sky, gently, endlessly, like something alive that's only sleeping. Let that sit with you a moment. Fountains of seawater off a moon you could hide in Arizona. It almost sounds made up. It isn't. We've seen it. We've flown through it. But we'll get to that. First, just look at it, because the thing about this moon, before anything else, before the oceans and the fountains and all the rest, the very first thing you'd notice if you could float up beside it is how astonishingly, impossibly bright it is. It is, as far as we know, the whitest world in the entire solar system, the most reflective. Of all the sunlight that reaches it, faint as that sunlight is so far from the sun, this moon throws back about 90% of it, almost all of it, bounces it straight back into the dark. Think about what that means. Nothing in your house is that white. Fresh snow on a winter morning, the kind that makes you squint, the kind that's almost too bright to look at. Even that doesn't reflect 90%. This moon is brighter than snow. A polished snowball hanging in the black of space. A mirror in the shape of a world. If you stood on its surface, the ground beneath your boots would be a clean, fresh, blinding white, stretching out in every direction, smoother and brighter than any field of snow you have ever walked across. And here's the gentle paradox of it. All that brightness, all that mirror shine throwing the sunlight away, it leaves the surface terribly, terribly cold. Because so little of the sun's warmth is ever absorbed, almost none of it soaks in. It all bounces off. So the surface sits at around minus 198 degrees Celsius, minus 330 Fahrenheit. A cold so deep it's hard to even hold in the mind. Cold enough that the ice there isn't soft or slushy or anything like the ice in your freezer. It's hard as stone. You could carve buildings out of it. The whole bright surface of this moon is rock-hard ice, polished and frozen and still, glittering in the faint, far sunlight, a polished snowball, mirror-bright, and colder than anywhere you will ever go. That's the outside of it. Hold that picture softly. It's a peaceful one, but the surface isn't quite featureless. Down near the south pole of this little moon, there are markings, 4 long cracks in the ice, running roughly parallel to each other, like the marks left by some enormous gentle claw drawn across the frozen ground. The scientists who first saw them, looking at the images coming back from out there, gave them a nickname. They called them the tiger stripes, and the name stuck because that's exactly what they look like. 4 great stripes scored into the bright white skin of the moon. But the tiger stripes have proper names too, and this is one of my favorite small details about this whole world. Each of the 4 was formally named. They're called Sulci, which simply means grooves or furrows, and each one was named after a city out of the Arabian Nights, the old book of bedtime stories. There's Alexandria, there's Cairo, there's Baghdad, and there's Damascus. 4 ancient cities of story and starlight, their names now carried across the solar system, written into the ice of a tiny moon at the edge of everything. Alexandria, Cairo, Baghdad, Damascus. 4 cracks near the bottom of the world, named for places out of a storybook, breathing water into the night. There's something fitting in that, I think, that the cracks where this moon does its strangest, most beautiful thing should be named after the cities where people once gathered, long ago, to tell each other tales in the dark until they fell asleep. As you're doing now in your own way, listening to a story about a faraway moon, letting it carry you down. And it's from those 4 cracks, from Alexandria and Cairo and Baghdad and Damascus, that the fountains rise. That's where the seawater escapes. Not from all over the moon, from there, from the warm wounds near the South Pole, the spray lifts off and drifts up into space. Which brings us, slowly, gently, to the real heart of this. The thing that makes this little bright moon one of the most extraordinary places we have ever found. Because if there are fountains of seawater, then there has to be water somewhere, liquid water, a sea. And there is. Beneath all that brilliant rock-hard ice wrapped right the way around the moon, sealed in the dark beneath the frozen shell, there is an ocean. A global ocean. A whole salty sea encircling the entire moon, hidden under the ice the way the yolk hides inside an egg. Not a lake, not a pocket. A complete ocean wrapping all the way around, sealed away from the cold and the dark of space above it. And you might wonder, fairly, how anyone could possibly know that. How can we say with any confidence that there's a whole ocean hidden inside a moon nobody has ever drilled into, nobody has ever landed on, nobody has ever seen beneath the ice? It's a lovely question, and the answer is one of those quiet, clever things that makes you smile when you understand it. They watched the moon wobble. As Enceladus turns slowly as it makes its way around Saturn, scientists measured its rotation very, very carefully. And they found a tiny wobble in it, a small, faint rocking back and forth, more than there should have been. And the only way to explain that little wobble, the only thing that fits, is if the icy outer shell of the moon isn't frozen all the way through. If instead that shell is floating, riding on a hidden layer of liquid underneath, cushioned by a sea, free to rock just slightly more than solid rock ever could, a moon frozen solid to its core wouldn't wobble like that. A moon with an ocean inside, with its icy crust gently afloat on hidden water, would. And this one does. That measurement, that careful watching of a small wobble in a distant moon, was published by a team of scientists in the journal Icarus back in 2016, Thomas and his colleagues. And it confirmed what the fountains had been hinting at all along. There's a sea in there, a real one. So picture it now, all of it together, as you lie there in the warm. A small, bright moon, smaller than a single state, the whitest thing we know of, colder than anywhere imaginable on its surface. And inside it, beneath miles of polished ice, a whole dark ocean of salt water wrapped all the way around, kept somehow liquid in the deepest cold. And down near the bottom of the world, 4 cracks named for ancient storybook cities where that hidden sea finds its way up and out, rising in slow, silent fountains into the black. And the next question, the one that settles in naturally after you've held that image for a moment, is a simple one. How? How does any of that happen? How does a moon made almost entirely of ice, sitting in the cold dark 1 billion kilometres from the sun, manage to keep a whole ocean liquid inside itself? How is there any warmth at all in a place that far from the fire? The answer, when you understand it, is one of those things that feels almost like a magic trick explained. Not less wonderful once you know how it works, more wonderful, because the mechanism is so elegant and so completely unlike anything that keeps our own world warm. Here on Earth we are warm because of the sun. We orbit close enough, at just the right distance, that the sun's light reaches us and heats our oceans and drives our weather and makes the air breathable. And there is also some warmth that comes from deep inside the Earth itself, left over from the violent heat of our planet's formation, slowly seeping out. But mainly, it is the sun, the big, bright furnace at the center of everything, 93 million miles away. That's what keeps us from freezing. Enceladus is not warm in that way. It cannot be. It sits so far from the sun that sunlight, by the time it reaches Saturn and its moons, is only about 1% as intense as what we feel here on Earth. And most of what does arrive, as you know now, bounces straight back off that mirror-white surface. Almost none of it is absorbed. The surface temperature down near the tiger stripes near the South Pole is warmer than the rest of the Moon, but the rest of the Moon is around minus 198 degrees Celsius. That is not a world being warmed by starlight. Something else entirely is happening. The answer is squeeze. Gentle, patient, ceaseless squeeze. Think about what happens when you bend a piece of metal back and forth, over and over again, the same spot repeatedly. The metal warms at the bend. You can feel it with your fingers. You haven't put it near a flame. You haven't done anything except flex it. The repeated deformation, the back and forth, generates heat from within. Heat from friction, from the material working against itself, from energy that began as motion turning through that resistance into warmth. Bend it long enough and it gets quite hot. Enceladus is bent. Not dramatically, not the way you might imagine a moon being squeezed by some great invisible fist, but gently, steadily, rhythmically as it orbits Saturn. Saturn is enormous. It is the second largest planet in the solar system, a world you could fit more than 700 Earths inside, and its gravity is immense. As Enceladus moves around Saturn, Saturn's gravity pulls on different parts of the little moon slightly differently. The side of Enceladus facing Saturn at any given moment feels a stronger pull than the side facing away. And as the moon moves along its orbit, as that near side shifts around, different parts of the moon are pulled just a little harder, just a little more. The shape of the moon flexes just slightly under that changing gravitational pull, stretched a little this way, pushed a little that, not enough to see with your eyes, but enough to matter. And all that flexing, all that slow, rhythmic deformation generates heat, friction deep inside the moon, warming it from within. This is what planetary scientists call tidal heating, and it is one of the more quietly astonishing ideas in the whole field of planetary science, because it means that gravity, the same gentle force that keeps you standing on the ground, that holds the moon in orbit around the Earth, that pulls water downhill, can, if the conditions are right, heat the interior of a small, distant moon well enough to keep a whole ocean liquid. The sun is not required. Distance from the star is not the only thing that matters. Gravity itself can be a source of warmth, but Saturn's pull alone might not be enough to keep Enceladus as active as it appears to be. That's where Dione comes in. Dione is another moon of Saturn, a quieter one, larger than Enceladus and further out. It keeps its own steady orbit further from Saturn, further from the heat and the activity. You might pass over it without a second thought, but Dione plays a crucial role in what happens to Enceladus, and it plays that role simply by being there, simply by following its own patient path. The two moons are locked in what is called an orbital resonance. It's a rhythm, a gravitational synchrony that arises naturally over long stretches of time when two orbiting bodies settle into a relationship where their orbital periods are in a neat whole number ratio. Enceladus orbits Saturn faster than Dione. It's closer in, and closer moons orbit faster, the way the inner horses of a merry-go-round complete their circles before the outer ones. And the ratio that has settled between them is 2 to 1. For every single orbit that Dione makes around Saturn, Enceladus completes exactly 2. 2 laps for every one, over and over, endlessly, in a rhythm as steady as a heartbeat. That sounds like mere bookkeeping of motion, a curiosity of orbital clockwork. But what it means in practice is that Dione and Enceladus regularly line up in the same configuration, that Dione's gravitational tug arrives on Enceladus's orbit not randomly, but in a repeating pattern, nudging the orbit slightly, keeping it from perfectly circular, keeping it gently stretched into an ellipse. And an ellipse is the key. Because when Enceladus's orbit is slightly elliptical rather than perfectly round, it moves a little closer to Saturn at one point in the orbit, and a little further away at another. It's a small difference, but it means the tidal pull of Saturn changes slightly as Enceladus moves around, stronger when closer, weaker when further. And that variation in the pull is what drives the flexing. Perfectly circular orbit, no variation, no flex, no heat. Slightly elliptical orbit, varying pull, flex, warmth. Dione, by maintaining that 2 to 1 rhythm, by nudging Enceladus's orbit back toward the ellipse every time it would try to circularize and relax, keeps the heating alive. There is something almost breathing about it when you think of it that way. A 3-body system, Saturn, Enceladus, Dione, locked in a slow repeating rhythm, Saturn pulling at Enceladus, Dione tugging it back into the slightly imperfect orbit that keeps the squeeze happening, and Enceladus yielding to it all, warming from the inside, keeping its ocean liquid, sending fountains up through the cracks, and through those cracks letting us know it is alive with warmth. The dance never stops. The resonance holds, the ocean persists, and now that you have that image, the mechanism of the warmth, you can understand something about the shape of things inside. Enceladus is small enough that its gravity is only enough to hold itself into a rough sphere. It is not so small that it's irregular and potato-shaped like some of the tiniest moons, but it's not a massive world with the gravity to compress its own interior dramatically. What you have, roughly, is a layered structure, a rocky core somewhere in the middle, then the ocean, a liquid saltwater layer wrapped around that core, and then the icy crust on the outside, the frozen shell that makes up the dazzling white surface we can see. The ocean is not a thin film. It is thought to be something in the region of 10 kilometres deep. 10 kilometres. For comparison, the deepest point in Earth's oceans, the Mariana Trench, goes down about 11 kilometres. So the ocean hidden inside Enceladus is, in depth, something broadly comparable to the deepest ocean trenches here on Earth. A full 10 kilometres of dark, cold, salty water wrapping all the way around a rocky core on a moon you could fit inside Arizona. It is a profoundly strange image, and a strangely beautiful one when it settles. On top of that ocean sits the ice, the crust, the shell. And here is something interesting about that shell. It is not the same thickness everywhere. On average, scientists estimate the ice is perhaps 20 to 25 kilometers thick. A substantial layer, much thicker than the ocean, is deep, which is part of why the warmth inside hasn't simply melted the whole thing away. But that average conceals an important variation. At the South Pole, where the tiger stripes are, where the fountains rise, where all the action is, the ice is much thinner. Only a few kilometers in some estimates. Thin enough in geological terms for the ocean water to find its way through, along those fractures, up through the cracks and out into space. Think of it as a pot sealed under a thick lid of ice slowly simmering. On most of the Moon, the lid is thick and the seal holds, but at the South Pole, the lid is thin, worn by the warmth that concentrates there, by the flexing that is most pronounced in the polar region, and so there the heat escapes and the water finds its path to the surface. The tiger stripes are not random. They are there because the ice is thin, because the warmth is greatest there, because the tidal flexing focuses its effects near the pole. The south polar region of Enceladus runs warmer than it should, and those four great cracks are the places where the warmth makes itself visible, where the interior of a moon becomes for a moment briefly an exterior thing. All of this was pieced together not by drilling through the ice. We have no way to do that from here, no probe sitting on the surface with a drill, but by careful measurement at a distance. The Cassini spacecraft, in its long years orbiting Saturn, used instruments to map the gravity of Enceladus, measuring subtle variations in the way Cassini itself was pulled as it moved. It used its cameras to measure the topography of the surface, the gentle rises and depressions. It used spectrometers to measure the heat leaking from the South Pole, the warm signature along the tiger stripes. All of these measurements, stitched together, built a picture of an interior that cannot be seen directly, but is as real for all that. The team that published the libration measurement, Thomas and colleagues, in Icarus in 2016, were watching the wobble as we talked about. And the wobble pointed to a decoupled shell, a floating crust, and the only way to get a floating crust is to have liquid underneath it. So the ocean is there, locked away beneath the ice, warm from the perpetual gentle kneading of orbital mechanics, and we know it from watching a small, patient wobble in the turn of a distant moon. Now, let's follow the water up. The geysers do not all stay on Enceladus. Most of the material that erupts through the tiger stripes falls back onto the moon's surface, like snow falling back to the ground after being blown upward by a gust. It settles softly on the ice around the South Pole, adding a fresh layer, another thin coat of clean new ice on top of what was already there. One of the reasons the South Polar region looks so fresh and smooth compared to the older cratered north. The fountain feeds itself in a way, but some of the plume material, a fraction, a portion light enough and fast enough, does not fall back. The plume particles leave the tiger stripe cracks at hundreds of meters per second. That is their speed when they emerge. And the key thing, the thing that allows them to escape altogether, is that Enceladus's gravity is so remarkably gentle. Gravity on the surface of Enceladus is approximately 1% of what you'd feel on Earth, just 1/100th. If you were standing there, you would weigh a fraction of what you weigh here. We'll come back to that image in a little while because it is a lovely one. But for now, what matters is what it means for the plume. A particle of ice or water vapor that emerges from the crack, moving at a few hundred meters per second, is moving well above Enceladus's escape velocity. Escape velocity is the speed you need to leave a world entirely, to travel fast enough that even as gravity pulls you back, you are always moving faster than it can drag you down. On Earth, you need to move at about 11 kilometres per second to escape. On Enceladus, because the moon is so small and its gravity so light, you need only a few hundred meters per second. And the plume particles hit that. They simply drift away, not with violence, not with any great dramatic launch into space. They drift. Like dandelion seeds caught in a breeze, if you'll allow the picture, rising out of the cracks, moving fast enough to escape, and then slowly, coasting outward into the empty space around Enceladus, carried by their own momentum, leaving a moon that can barely hold them. And where do they go? They go into a ring. Saturn has rings. You know that. Even a child knows that. Saturn's rings are one of the most recognizable images in all of astronomy. The great flat disk of ice and rock that circles the planet in its equatorial plane. The rings that you can see through a modest backyard telescope, the rings that have been painted and photographed and marveled at for centuries. The main rings, the A ring, the B ring, the C ring, the ones you picture when you picture Saturn, are made of material ranging in size from tiny dust grains to chunks of ice as big as a house, and they orbit in the planet's equatorial plane and catch the light and glow. But Saturn also has fainter rings, thinner and more diffuse, further out from the planet, and one of them is called the E ring. The E ring is not like the main rings. It is not a dense, bright, flat sheet of material. It is faint and broad and diffuse, like smoke compared to the main ring's polished metal. It stretches out far from the planet, a vast and gauzy ring of tiny ice particles, too small and too spread out to see easily without the right instruments. And it is very specifically not ancient, not a ring made of material that has been there since the beginning of the solar system. It is new material, continuously replaced, because the E-ring leaks. The tiny ice particles in the E-ring are small and light, and they are slowly pushed around by the pressure of sunlight, a gentle nudge called radiation pressure, and by interactions with Saturn's magnetic field and the charged particles around the planet, and by the same kind of tidal forces we've been talking about. And all of those nudges over time gradually shift the particles out of the ring and scatter them. If nothing replaced them, the E-ring would fade, it would thin and spread, and eventually be gone. And yet it persists. It persists because Enceladus is sitting right inside it, continuously breathing new material into it. The plume particles that escape Enceladus drift into the region where the E-ring exists, and they join it, and they replenish the material that leaks away. Enceladus is the source. Enceladus feeds the ring. Roughly 200 kilograms of water leave the moon every second as plume material, and a portion of that makes its way into the E-ring and keeps it going, keeps the gauzy, faint halo around Saturn alive. This was published by Spahn and colleagues in the journal Science in 2006, and it tied a neat bow around something that had puzzled scientists for years: why the E-ring existed at all, and why it was concentrated in exactly the region where Enceladus orbits. Now here is the part that I find particularly lovely, and I hope it finds you the same way. Enceladus doesn't just feed the ring from the outside. Enceladus orbits within the E-ring. The little moon sits inside the very cloud of material that it created, that it has been producing and releasing for a very long time. It swims through its own ring. Every time Enceladus completes one of its short 32.5-hour orbits around Saturn, it moves through a diffuse haze of particles that were once inside it. The water that was, not long ago, part of that hidden subsurface ocean that rose up through the tiger stripes and floated away into space, now drifts gently around Enceladus in the E-ring as the moon passes through. The moon and the ring are made of the same water, cycling between two different states of existence, the solid and liquid below and the drifting vapor and ice above. And some of those particles come back. Not all of the ones that enter the E-ring stay there forever. Some drift back and settle onto the surface of Enceladus itself, adding to the fresh coating of ice that makes the moon so improbably white. And some drift further, onto neighbouring moons. Saturn has many moons, and Enceladus sits among them, and the fine mist of material from the E-ring gently dusts the surfaces of nearby moons with clean white ice, settling like the quietest imaginable snowfall. Snow in space. On moons, the product of a subsurface ocean venting through cracks in a tiny ice world, rising into space, spreading across a ring, and then slowly, quietly descending again. There is a slowness to it, a patience to it that I find genuinely calming. It is not dramatic. No explosion, no collision, no catastrophe. Just a continuous quiet exhalation from the inside of a moon, a gentle dispersal of water into the neighborhood, a slow, gentle whitening of surfaces nearby. Enceladus has been doing this for a long time, long enough to have built a ring, long enough to have kept it replenished, long enough to have kept itself mirror bright with its own returning snow, because that's part of why Enceladus is so bright. Not only because its surface is clean ice to begin with, but because it is continually recoated with fresh material. The old ice gets a new dusting, and the new dusting reflects as well as the old, and so the brightness is maintained. The moon refreshes itself, keeps itself white the way a snowfield stays white when fresh snow keeps falling. Only here the snow is the moon's own exhaled water, rising and returning, rising and returning. Wherever you are right now, whatever the light is like around you, a lamp in the corner, the blue glow of a screen dimming slowly, the darkness of a room where the curtains have been drawn. Try to hold this picture for a moment. A small, bright moon, 1 billion kilometres away, quietly breathing salt water into the black, sending plumes of ice drifting into a ring around a giant ringed planet, the ring material settling back as snow, the moon staying white, the ocean staying warm, the rhythm never stopping. 200 kilograms every second, as naturally and continuously as breathing, as unhurried as a tide. It has been doing this for longer than there have been trees on Earth, possibly longer than there has been complex life anywhere we know of. And when you wake up tomorrow morning and the sun comes through the curtains and the ordinary world reassembles itself around you, Enceladus will still be doing it. While you sleep, while you work, while years pass and decades pass and you grow and change, and the world around you shifts. Out there, the plumes will still be rising. The ring will still be faintly glowing. The snow will still be falling very softly on the surface of a moon you will likely never see with your naked eye, but that is no less real for that. A day on Enceladus lasts about 32.5 hours, just a little longer than a day here, though of course it is not a day in any sense we would recognize, because there is no sun to rise and set in any meaningful way at those depths of the solar system, but the moon turns at that rate, completing its own slow rotation in that time, and because Enceladus is tidally locked, the same face always turned toward Saturn, just as our own moon keeps one face always toward us. A full rotation and a full orbit are the same thing. The 32.5 hours it takes to spin once around is the same 32.5 hours it takes to complete one orbit of Saturn. The moon and the planet face each other in an eternal, patient gaze. From the Saturn-facing side of Enceladus, the planet would hang in the sky, enormous and still, the great rings cutting across the view. Saturn would not rise or set. It would simply be there, always, enormous and ringed and beautiful, filling a large portion of the sky, its cloud band shifting with Saturn's own faster rotation below. A fixed companion, an immovable presence. If you were standing on that face of the moon, in some imagined, impossible scenario, wrapped in something that could keep you warm in the -198-degree cold, breathing through something that could function in the near vacuum, you would always be able to look up and find Saturn exactly where it had always been. But we are drifting just slightly into something you do not need to concentrate on or follow carefully. It is just a picture, a Saturn, enormous and striped and ringed, hanging still in the sky above a small, bright moon whose south pole is quietly steaming. That is all. A picture to carry into sleep. Let's stay with the moon itself for a moment, and with what happens at its surface. Because the south is not the only part of Enceladus worth thinking about quietly. The south, as we've talked about, is young, geologically young, which in planetary science means that the surface has been replaced relatively recently, wiped clean and repaved with fresh ice by the ongoing activity by the settling of plume material, by the heat from below pushing up through the cracks and smoothing what was there. The south pole of Enceladus has very few craters. Impact craters are what accumulate on a surface over time, rocks from space hitting the moon, leaving their round marks, building up over billions of years into a record of how old and inactive a surface is. A heavily cratered surface is an old, inactive surface. The cratering tells you the surface has just been sitting there, undisturbed, accumulating hits over geological time. The south of Enceladus tells you almost nothing by that measure, because whatever craters might have accumulated there, the activity has covered them, smoothed them over, replaced the surface with something fresh. The south polar region looks almost new, like a page that has been carefully, slowly rewritten over whatever was there before. The north is different. The north is old. The north of Enceladus is cratered in the way you'd expect from a world that has been largely undisturbed for a very long time, hit again and again over billions of years of solar system history, each impact leaving its quiet, circular mark. The north is the moon's memory, and the south is the moon's present, its activity, its ongoing life. Two faces of the same small moon, one ancient, one fresh, one quiet, one exhaling, one keeping its record of the past intact, one being continually rewritten by the warmth below. The boundary between the two, the place where the old cratered terrain gives way to the younger, smoother, more geologically active terrain, is itself one of the interesting features of Enceladus. A place where two entirely different expressions of a moon's life meet, separated by whatever process of tectonic adjustment or geological transition occurs in a world whose interior is warm enough to keep an ocean, but whose surface is cold enough to freeze solid. The Cassini cameras photographed all of it, building up slowly over years of flybys, a detailed picture of a surface that is in conversation with its own interior. And through all of those flybys, as Cassini orbited Saturn and periodically swooped near Enceladus, the plumes kept going, continuously. Season after season of Saturn's long year, and Saturn's year is nearly 30. Earth years long, so seasons there are long, slow, patient things. The plumes kept rising from the tiger stripes. Not the same intensity every time, perhaps, varying somewhat with the changing tidal stresses as Enceladus moved through different points of its slightly elliptical orbit, but persistent. Always present, a small moon breathing 200 kilograms of water every second. That is the estimate. And it is worth sitting with because it is a curiously easy number to picture. 200 kilograms is roughly the weight of 3 large adults, or of a large piece of furniture, or of a few suitcases packed heavily for a long trip. And every second, every single second without pause or rest, that weight in water leaves Enceladus in the form of plume material, rising from the tiger stripe cracks, drifting upward and outward, some falling back, some going into the ring, some going into space. It has been doing this, as far as we can tell, for a very long time. The rate might vary, it might have been higher or lower at different points in the moon's history, but the basic picture, a continuous, patient, unceasing exhalation of water from a hidden ocean, is one that has apparently been running for an extraordinary span of time. Longer, very likely, than there have been mountains on Earth in their current form. Longer than there has been ice at the poles. Longer, possibly, than complex life has existed anywhere we know of. The fountain has been running while everything we know of living history on this planet unfolded. Enceladus was breathing while the dinosaurs lived and died and vanished. It was breathing when the first humans looked up at Saturn and wondered. It was breathing when William Herschel in 1789 pointed the greatest telescope in the world at the sky and noticed a faint dot circling that ringed planet and wrote it down and gave it a name. It was breathing last night while you were awake, and it is breathing now while you are settling towards sleep. The fountain does not need you to witness it. It runs regardless, and the ring persists. The faint E-ring, the ghost ring, the one made of Enceladus's exhaled water, continues to diffuse around Saturn in that broad, gauzy halo. Scientists can observe it. Cassini photographed it extensively, measuring its composition, its extent, its structure, and confirming clearly and directly that the material in the E-ring is the same material coming out of the plumes. The fingerprints match. The ice particles in the ring have the right composition, the right size distribution, the right properties to be Enceladus's breath, and so a picture assembled itself piece by piece over years of Cassini data, of a small moon building and maintaining one of the rings of a giant planet from the inside out. A moon so active, so continuously productive, so endlessly generous with its water that a ring formed in the space around it and persists and would fade and vanish if the moon went quiet. If the tidal heating stopped, if somehow the resonance with Dione were broken, if the orbit circularized, if the flexing ceased, the ocean would eventually cool and freeze. The plumes would slow and stop. The E-ring would thin and disperse, the particles drifting away over thousands or tens of thousands of years until the ring was gone. Saturn would still have its main rings, bright and dramatic, in the inner system, but the E-ring, the one born from a hidden ocean on a tiny moon, would be gone. But that hasn't happened. The resonance holds. The heating continues. The ocean is liquid tonight. The plumes are rising. The ring is there. Let the whole system settle in your mind slowly, like the snow that falls on Enceladus's own surface. Saturn at the center, vast and patient. Dione in its outer orbit, pulling on Enceladus's path with gentle gravitational insistence, once per 2 Enceladian orbits, keeping the slight ellipse alive. Enceladus flexing in Saturn's gravity, warming from within, hiding a 10-kilometre deep ocean beneath 20 or more kilometres of ice, that ice thinning to just a few kilometres at the South Pole, where 4 great cracks open to the dark sky. Water rising through those cracks at hundreds of meters per second, light enough to escape a moon with only 1% of Earth's gravity, drifting into the ring that the moon itself has made, the ring that wraps gently around Saturn in the space where the moon orbits, the moon passing through the ring it built, snow settling back down. A closed loop of water moving between inside and outside, between hidden and visible, between liquid and frozen and liquid again. A cycle running on the borrowed energy of gravity, a gravitational engine that turns the squeeze of orbital mechanics into heat, and heat into ocean, and ocean into fountains, and fountains into rings, and rings into snow, and snow into brightness, and brightness into the most reflective world we know. All of this on a moon small enough to fit inside a single state. If you are still awake, I'm genuinely glad to still have your company. And if you are drifting, that is exactly as it should be. There is nothing here you need to hold on to. The facts are not going anywhere. Enceladus will still be there when you wake, still breathing, still bright, still swimming through its own ring. The ocean under the ice won't have changed between now and morning. You can let it all become background, and it's a warm sense that somewhere out there, something small and bright is quietly doing something extraordinary. And let that sense carry you gently under. Because we're not done with what Cassini found. There is still more to tell you, and it is some of the most quietly astonishing material in planetary science. What was in those plumes once a spacecraft flew directly through them and tasted them. That is where the story goes next. What the ocean of Enceladus turned out to be made of, what was found in its spray, what those findings mean for the oldest question that humans have ever asked about the universe. All of that is waiting softly on the other side of sleep. For now, though, rest with the ring. Rest with the image of 200 kilograms of water leaving a tiny moon every second, floating outward into a gauzy halo of ice around a distant giant planet, and some of it falling back as snow. Rest with the knowledge that the ocean is down there, warm, dark, wrapped around a rocky core, sealed beneath the ice, kept liquid by the gentle squeeze of a dance between three bodies, a planet, a moon, and another moon, that has been going on for longer than we have been here to watch it. That is already more than enough wonder for one night, or for the beginning of sleep. You have it now, somewhere in you, even if the details blur and soften and run together in the warm, half-conscious way that facts do when you're nearly asleep. The image remains even when the specifics go. A small, bright moon, a hidden ocean, a ring made of its own water, a fountain that has never stopped. Rest now if you can. We'll continue when you're ready. And so we follow the spray. We follow it back to its source, down through the dark, past the bright surface of ice, past the tiger stripes named for those ancient cities, past the rim of the fractures where the warm water rises, and we go, in our imagination, all the way back to the moment a spacecraft first did this for real. When something human-made, something we built and launched and guided across the solar system, plunged directly into those fountains and opened its instruments, like cupped hands, to catch whatever was rising out of that hidden world. That moment happened on the 14th of October in the year 2015. The spacecraft was Cassini, and what it did was fly straight through the plume, not past it, not alongside it, through it, into the spray rising from those tiger-striped cracks at the south pole of Enceladus down to within 49 kilometres of the surface, which, given the scale of things out there, is like putting your face close to a steaming kettle and breathing in, not looking at it from across the room, breathing in. 49 kilometres, 30 miles roughly in the terms you might use to measure a drive between towns, a short drive, a quiet Sunday distance. And yet this was a spacecraft moving at tremendous speed through a fountain erupting from a moon 1 billion kilometres from the sun, and it had its instruments open the whole time, and it was collecting data, and it was, in the truest possible sense, tasting an ocean it never touched. Let that settle a moment before we go further. No spacecraft had ever done this before. To sample the ocean of another world, scientists had assumed you would need to land, to drill, to bore down through kilometers of ice with specialized equipment and lower something down into the dark. That was the plan, in the abstract. It would take decades of engineering and enormous cost and the kind of mission complexity that makes even the most experienced planetary scientists go quiet when they contemplate it. And then Enceladus simply offered its ocean up. The moon itself sent the sample into space. It shot it upward, through its own crust, through those 4 glowing fractures, out into the vacuum, and Cassini flew through it and caught it. The ocean came up to meet the spacecraft. No drilling required, no landing, no surface mission, no kilometer-long borehole. The ocean of Enceladus extended itself outward into space, and we flew a machine through it, and we found out what it was made of. That is, quietly, one of the most remarkable things that has happened in the history of space exploration. Not the loudest, not the most dramatic on television, but remarkable in a deep, structural way. The way certain pieces of luck are remarkable, not because you planned them, but because the universe happened to arrange itself in exactly the right configuration for you to ask a question and receive an answer you couldn't have retrieved any other way. Enceladus gave us that. And what did the instruments find when Cassini flew through the plume and held out its sensors into the rushing spray? Water, of course. An enormous amount of water. The plume is, at its core, steam and ice and water vapor, molecules of H2O in every phase, pouring out of those cracks and rising into the dark. That was expected, more or less, by that point. The plumes had been known since 2005. The presence of water was not the surprise was everything else. In the plume, among the water and ice, Cassini's instruments found salt. Sodium chloride. The same compound you might have sitting in a small white container on your kitchen table at this very moment. The ordinary mineral that seasons food and preserves it and runs through your own blood and tears. Common, familiar, unremarkable on Earth. On Enceladus it was astonishing, because salt, dissolved in water the way ocean salt dissolves, doesn't just appear on its own. It gets there through geological processes. Water moving over rock, dissolving minerals, carrying those minerals into solution, becoming brine. The salt in Enceladus's plume meant the ocean beneath the ice had been in contact with rock, not just sitting in a cavity lined with ice above and below, but actually touching the rocky floor of the moon, interacting with it, chemically exchanging with it, the way water and rock exchange down at the bottom of Earth's oceans. That was the first clue. The instruments also found carbon dioxide and methane and ammonia and molecular hydrogen, a whole vocabulary of molecules rising up in the plume, carried out of the subsurface ocean and into space, and, on this particular flyby, into the open instruments of a spacecraft we had sent to find out what was there. Each of these is worth pausing over, not racing through, not listing and moving on. Each one is a small piece of a picture, and the picture takes a moment to see. Carbon dioxide, you breathe it out, plants take it in. In a planetary context, its presence in a subsurface ocean is consistent with a chemically active environment, not just a cold, inert pocket of water, but a place where reactions are happening, where compounds form and dissolve and reform, where the water is doing something. Methane. A simple molecule. 4 hydrogen atoms around 1 carbon atom. On Earth it is produced by many things, by geological processes and also notably by biology. Life makes methane. Many microbes make methane. The presence of methane in the plume does not mean life is present. It can form through non-biological chemistry too, and the scientific consensus is careful about this. But it is one of those molecules that sits at the intersection of geology and biology, a molecule you would pay attention to if you were searching for signs of either. Ammonia. 3 hydrogen atoms around a nitrogen atom. Present in many icy moons, often incorporated into the ice itself during the early formation of the solar system. In Enceladus's ocean, ammonia may play a role in keeping the water liquid at lower temperatures. It acts as a kind of antifreeze, lowering the freezing point of water and helping the ocean stay fluid even in the extreme cold of deep space. And then, molecular hydrogen. Hydrogen, H2, 2 hydrogen atoms bonded together, one of the simplest molecules in the universe and one of the most important in the context of what Cassini was finding. Here is why molecular hydrogen matters, and it matters in a way that is worth telling slowly, because it is one of those connections that feels, when you first understand it, like a tiny door opening in your mind. On Earth, in the deepest parts of the ocean floor, there are places called hydrothermal vents. You've perhaps heard of them. They are cracks in the seafloor, places where seawater percolates down into the hot rock beneath the ocean floor, gets heated, and rises back up carrying dissolved minerals and gases. They come in different varieties. The hot, acidic black smokers and the somewhat cooler, more alkaline systems called white smokers, among others. Around these vents, in complete darkness, with no sunlight ever reaching them, communities of living things exist: microbes, tube worms, shrimp. Strange, soft creatures that have no need for the sun at all. They live not on sunlight, but on chemistry. Specifically, on the chemical energy released when certain reactions happen between the vent fluids and the surrounding seawater. One of the most important of these reactions involves molecular hydrogen. When water at high temperatures reacts with certain kinds of rock, particularly iron and magnesium-rich rocks, a chemical process called serpentinization occurs. Water molecules interact with minerals in the rock, and in the process, molecular hydrogen is released. That hydrogen then becomes available as a chemical energy source. Microbes at hydrothermal vents on Earth use this hydrogen, combining it with carbon dioxide to make organic matter and releasing methane as a byproduct. They are, in a very real sense, eating rock and water chemistry. They are living on the energy stored in geological processes. This is not speculation. This is well-established biology observed in Earth's own oceans. Now, Cassini flew through the plume of Enceladus and found molecular hydrogen. The presence of that molecular hydrogen you could get in the plume, coming from the ocean, tells scientists something specific, that somewhere in Enceladus's interior, hot water is reacting with rock in a process consistent with serpentinization. That there are almost certainly hydrothermal vents on the seafloor of that hidden moon, that the same basic geological mechanism that drives some of Earth's deepest, most resilient ecosystems appears to be operating right now in an ocean sealed beneath the ice of a world 1 billion kilometres from the Sun. This was reported in the journal Science in 2017. The lead author was J. Hunter Waite from the Southwest Research Institute, and the team behind it had spent years analysing the data from Cassini's plume flybys. The paper was careful, precise and calm in the way good science is calm. It said, we found molecular hydrogen. It said, the most likely explanation is water-rock reactions in the subsurface, consistent with hydrothermal activity. It said, this is significant for the question of habitability. It did not say, there is life. It said, the conditions are there for the kind of chemistry life uses. That distinction matters, and it's worth naming it clearly so you can rest with the right picture. Habitability means the conditions that could support life, not that life exists. A newly built house is habitable whether or not anyone has moved in yet. Enceladus appears to be habitable in this sense. It has the conditions. Whether anything is living there, no one knows. No one has found life, no signals, no organisms, no confirmed biological signatures have been detected. Only the raw materials and the energy source and the liquid water. Only every ingredient on the list present and accounted for in a dark, warm sea beneath a frozen shell on a small, bright moon. You can sit with that without it needing to be resolved. The not knowing is its own kind of wonder. A held question, gently held, not anxiously. But there is more that Cassini found, and it comes in the form of something very small and very specific. Silica. Silicon dioxide, or indeed the same compound that makes up quartz and sand and glass. Tiny, tiny grains of it found in the plume data. So small as to be invisible, little more than dust drifting in the spray. And yet their presence is a precise fingerprint. The reason these silica grains are significant is not just that they are there, but how they form. Silicon dioxide precipitates, falls out of solution, crystallizes into particles, only under specific conditions. Only when water that has been heated to above about 90 degrees Celsius interacts with silica-rich rock, and then, crucially, when that hot fluid cools and the silica can no longer stay, dissolved and drops out as tiny solid grains. The size of those grains depends on the chemistry and the temperature history of the fluid they came from. What Cassini found were nanometer-scale silica grains, incredibly fine, of a specific size consistent with forming in high-temperature, alkaline hydrothermal conditions. This was the finding reported by Xiang Wensu and colleagues in the journal Nature in 2015, and it is, in a quiet way, one of the most direct pieces of evidence we have for what is happening at the floor of Enceladus's ocean. The message written in those silica grains is this: somewhere down at the bottom of that hidden sea, hot water, hot enough to brew tea by human standards, hot enough to be well above boiling point in some models, is flowing through or over silica-rich rock. The rock is being chemically altered. Hot, mineral-rich fluids are rising from the seafloor, just as they rise from hydrothermal vents at the bottom of Earth's oceans, and those fluids carry silica up into the water column, and the silica cools as it rises and precipitates out as tiny grains. And those grains eventually, over time, work their way out through the tiger stripes, into the plume and into space, and Cassini caught them. A spacecraft in orbit around Saturn found tiny grains of sand from the bottom of an alien ocean, carried upward through kilometres of water and ice and out into the vacuum. Found them, measured them, and from their size and composition told us, indirectly but convincingly, what the seafloor of Enceladus is doing. That is extraordinary. Hold that for a moment, not with urgency, just with the quiet appreciation it deserves. The seafloor of a moon you will never stand on, around a planet you will never visit, speaking its chemistry upward through its own crust, and out into the dark, where we were waiting to listen. And what do we compare this to? The hydrothermal vents of Earth. The ones on our ocean floors are among the most extraordinary environments on this planet. They were not discovered until 1977, not so long ago, when a research submersible dove to the Galapagos Rift in the eastern Pacific and found, to the astonishment of the scientists aboard, entire thriving communities of life in the complete absence of sunlight. Tube worms 2 meters long, clusters of blind white shrimp, mats of bacteria covering every surface, all of it alive and dense and active in the pitch-dark cold of the deep ocean. All of it living on chemistry, not light. This changed how biologists and planetary scientists thought about life. Before 1977, the working assumption was essentially, life needs sunlight. Life depends on photosynthesis. Life begins in the shallow, warm, sunlit zones where plants and algae can grow and begin the chain that eventually feeds everything else. The deep ocean, in this model, was peripheral, cold, dark, and mostly dead. The vents revealed that the model was too small. Life is more flexible than that. Life, it turns out, is willing to go to the dark and the deep and the hot and find what energy there is and use it. The chemical energy of rock reacting with water is enough, has always been enough for something. And now Enceladus shows us silica grains formed in conditions consistent with those vents, and molecular hydrogen of the kind those vents produce, and salt from water interacting with rock, and carbon-rich molecules, and methane. The deep ocean of Earth translated into the dark interior of a small ice moon far out in the cold of the solar system around a planet with rings. The similarity is not proof of anything. Similarity is not identity, but it is a door held gently open, the suggestion that the kind of chemistry that here on Earth led to some of the most resilient and ancient forms of life is running on another world. Right now. While you lie there, wherever you are, in whatever kind of night surrounds you. Down in the dark of Enceladus, kilometres beneath the ice in a warm saltwater sea, hydrothermal chemistry is happening. Hot water is moving through rock. Molecular hydrogen is being released. Silica grains are forming and rising. The plume is feeding the ring. Whether anything is alive in that ocean to notice any of it, we don't know. But the kitchen is stocked. The conditions are there. The door is, at minimum, unlocked. And there is something genuinely calming about that if you let it be. Not because the answer is known, it isn't, but because it means the universe is more generous with the ingredients for life than we once thought. A moon we barely knew existed until Cassini arrived. A plume found almost by accident because a magnetometer noticed the magnetic field bending where it shouldn't. And in that accidental, unplanned discovery, an ocean with salt, with warmth, with energy, with chemistry, a world that perhaps hosts life and perhaps doesn't, and either way is extraordinary. The molecular hydrogen discovery, as reported by Waite and colleagues in 2017, described the reaction in terms of what it could theoretically support. The type of chemical reaction involved, hydrogen reacting with carbon dioxide to produce methane and water, a process known as methanogenesis, is one of the most ancient forms of energy metabolism known on Earth. Some of the oldest lineages of microbes on this planet are methanogens. They live on this chemistry. They live in deep rock, in hydrothermal systems, in environments with no light, no oxygen, and no complexity, just hydrogen and carbon dioxide, and the slow, quiet chemistry of making methane. The researchers noted that the discovery does not confirm life. They were careful about this. But they noted that if methanogenic microbes existed in Enceladus's ocean, the hydrogen and carbon dioxide they found would, in principle, support them. The raw fuel would be there. What does that feel like to contemplate, quietly, in the dark, before sleep? It feels like, if you can let it settle softly, the universe writing the same story in different places. The same chemical logic, repeated. Water and rock, given enough time, tending toward conditions where something called life becomes, at minimum, chemically possible, not inevitable, not guaranteed, but possible. And the distance between possible and actual is exactly where every form of life we've ever found exists. On the far side of that threshold, in conditions that allowed it. Enceladus sits at the threshold. Warm water, chemical energy, the right molecules. Just on the near side of that line, or perhaps already across it, in the dark, in some form we haven't yet seen. Gently, not urgently, as a wondering. And the molecular hydrogen tells us something else, too, something more structural about what Enceladus is doing geologically. Serpentinization, the water-rock reaction that produces the hydrogen, tends to happen in rocks called ultramafic rocks, rocks rich in iron and magnesium. These are common in the deep interiors of rocky worlds, and they react with water in a specific way that releases hydrogen as a chemical byproduct. The fact that this reaction appears to be happening at the floor of Enceladus's ocean means that the ocean is not just sitting on bare ice or simple silicate rock. It is in contact with rock that reacts chemically with water in an ongoing, sustained way. This also means the ocean is not static, not a sealed, inert lake. It is a chemically active environment where water and rock are constantly exchanging, where minerals are being dissolved and precipitated, where the composition of the water is being shaped by the geological activity beneath it. A living ocean in the geological sense, alive with chemistry, even if it is not alive with biology. The warmth that drives this comes ultimately from tidal heating, from the same gravitational squeezing that we spoke of before, the kneading from Saturn and from Dione, keeping the interior of the moon warm enough for liquid water, warm enough for hydrothermal activity, warm enough to sustain the reactions that produce molecular hydrogen and carry silica to the surface and keep the plumes going. It is all connected, the orbital resonance with Dione, the tidal heating, the liquid ocean, the warm seafloor, the hydrothermal chemistry, the molecular hydrogen, the silica grains, the plume, the spray into space. Cassini catching all of it in a single pass, 49 kilometres above the ice. A chain of connections from the orbit of a moon around a ringed planet all the way down to the chemistry of water reacting with rock in the dark. And back up, again, into the spray, and into the instruments of a spacecraft we sent there, and into the pages of scientific journals, and now, in some softer, more diffuse way, into you lying there, letting it settle. You don't have to hold all of it precisely. The chain is there whether you remember every link or not. The facts are true whether you're fully awake to receive them or half dissolved into sleep. They'll still be true when you wake up. The plume is still running even now, even tonight, sending water and salt and silica and hydrogen out into the dark around Saturn. That's a kind of permanence, a kind of constancy. Something in the universe that keeps going regardless of whether you're watching. Cassini flew through the plume multiple times over its years in the Saturn system. The October 2015 flyby was particularly close, the E-21 dive, as mission scientists designated it, the one that brought the spacecraft down to 49 kilometers. But there were other passes too, at different altitudes and angles, each adding a piece to the picture. The instruments on board the spacecraft were varied and complementary. Mass spectrometers that identified molecules by their mass, a dust analyzer that captured and analyzed individual particles, a magnetometer that tracked the magnetic field, cameras that resolved the jets themselves into visible columns of light rising from the South Pole. The plumes, seen through Cassini's cameras, looked like long, faint threads of light, rising from the tiger stripes in the darkness of the moon's south polar night, catching the distant sunlight and glowing softly, like the finest mist backlit by a low lamp. Multiple jets from multiple locations along the fractures, braiding together as they rise, merging into the broad, diffuse column of the overall plume. Quiet, continuous, patient. The spacecraft that found all of this was itself, in a quiet way, a remarkable thing. Cassini was a joint mission between NASA and the European Space Agency and the Italian Space Agency. It launched in 1997 and arrived at Saturn in 2004, having traveled nearly 7 years through the solar system. It spent 13 years in orbit around Saturn, 13 years measuring, photographing, sampling, gradually building up the extraordinary picture we now have of that planet and its many moons. And when its fuel finally ran low in September 2017, mission controllers made the decision to plunge it into Saturn's atmosphere, destroying it rather than risk it contaminating one of the moons, particularly Enceladus, with its potentially life-supporting ocean. They did it with biological material from Earth. Cassini ended its mission by diving into the planet it had spent 13 years studying. It transmitted data all the way down until the atmosphere finally claimed it. It gave everything it had to the very last moment. There is something gentle in that ending. A spacecraft that found an alien ocean and then sacrificed itself rather than risk contaminating it with the world that built it. A small act of planetary hygiene, a kind of respect encoded in the mission design. And now the data it gathered continues to be analyzed. Papers continue to be published. Each new study finds new things in the observations Cassini made, new patterns in the plume, new constraints on the ocean's chemistry, new models of the hydrothermal system. Cassini is gone, but the science it produced is still unfolding, still deepening, still asking questions that its instruments answered from hundreds of millions of kilometers away. The molecular hydrogen, the silica, the salt, the organic molecules, all of it collected in those plume flybys, carried in the data streams back to Earth, processed and analyzed and published in journals and discussed at conferences and slowly, over years, assembled into a picture. The picture is this. Enceladus has a global liquid ocean of salt water. That ocean sits on a rocky seafloor. The seafloor is geothermally active, with hydrothermal vents or vent-like systems releasing warm water and molecular hydrogen and silica into the ocean. The chemistry of that ocean includes every major category of molecule that life on Earth requires as raw material, and the whole system is sustained by the gravitational energy of Saturn and Dione, endlessly squeezing the Moon as it orbits, keeping the interior warm, keeping the chemistry going. That picture was not available before Cassini. Before Cassini arrived at Saturn, Enceladus was considered an interesting but relatively minor moon, small, bright, and probably geologically dead. Voyager had photographed it in 1980 and 1981, and even then something had seemed unusual about its surface, too smooth and too bright to be explained by simple passive cratering. But the explanation had to wait for Cassini, had to wait for a spacecraft that would get close enough to see the jets, to fly through the plume, to taste the spray. And when it did, what it found quietly rewrote what a small, cold moon in the outer solar system could be. It could be this, a moon that breathes seawater into the sky, that keeps a hidden ocean warm in the dark, that writes its own chemistry in a plume of ice and vapor and sends it outward as an invitation or as a gift, or perhaps as nothing at all. Just the physics of a warm, pressurized system venting through cracks in a frozen shell, without any intention, without any awareness, without any purpose, beyond the simple fact of what the physics requires. But the physics, in this case, produces something that looks to us like generosity. An ocean offered up for sampling, a chemistry textbook written in spray. Somewhere between the silica grains and the molecular hydrogen, in the data from a spacecraft that flew 49 kilometers above a frozen moon in October 2015, is one of the most extraordinary things discovered in planetary science in recent memory. And you know about it now. Let the hydrogen settle, let the silica grains drift down, let the plume rise from those Arabian Nights, cracks in the ice, into the dark, patient and continuous, carrying its salt and its molecules and its warmth upward from the hidden sea. The ocean is there, the chemistry is there, the hydrothermal warmth is there. And somewhere in the data that Cassini carried home, the beginning of a question that may take another generation to answer, or may never be answered, and may rest forever as a wondering, as a gentle, open possibility, as the kind of not knowing that is not unsettling, but merely vast. A small moon in the outer solar system quietly keeping its ocean warm, quietly venting its chemistry into space, quietly waiting, if waiting is even a meaningful word for something that has no awareness of time, for someone to come and ask the right questions. Cassini asked some of them, the answers were astonishing, and there are more answers yet to come in the chemistry of those plumes, in the details of those silica grains, in the precise composition of the water that rises from the seafloor of an ocean we have never directly seen and can only know through the spray it sends outward into the dark. More of that is waiting. In the chemistry of life, in the larger organic molecules found later in the plume, in the phosphorus discovered in 2023, in the full accounting of every ingredient that life requires, checked off one by one from the list. All of that is still ahead in this story, still to be told softly in the same quiet way. But for now, rest with the hydrogen, rest with the silica, rest with the image of Cassini dropping toward that south polar ice at 49 kilometers distance and opening its instruments into the spray and tasting, for the first time in human history, the interior of another world's ocean. And what a taste it was, because the hydrogen and the silica were only the beginning. The plume that Cassini flew through was not simple. It was not just water and salt and a few small molecules. It was, as it turned out, carrying something more, something that the instruments on board registered and that scientists, going over the data carefully, found waiting for them in the numbers. In 2018, 3 years after Cassini's closest dive and 1 year after the spacecraft had completed its mission and fallen, deliberately, into Saturn's atmosphere, gone, its work done, preserved from contaminating the very moons it had studied, a team led by Frank Postberg published findings in the journal Nature. They had been working through the data from the Cosmic Dust Analyzer, the instrument aboard Cassini that caught and catalogued individual particles as the spacecraft passed through the plume. And in those particles, in the ice grains, sampled during multiple flybys over years of close passes, they found something: large, organic molecules. Not simple ones, not methane, which is just 1 carbon and 4 hydrogens, small and light, and already remarkable enough. These were complex carbon-rich molecules, the kind with many atoms chained together, the kind that on Earth we associate with the building blocks of biological processes, the raw materials from which chemistry becomes complicated and, in some circumstances, alive. Let that sit for a moment, softly. Complex organic molecules. Rising from the seafloor of an ocean on a moon 1 billion kilometres from the sun, carried upward through the liquid water, emerging through the ice cracks at the South Pole, riding the plume into space, and there, drifting in the cold and dark around Saturn, intercepted by a spacecraft that had been sent from Earth precisely to ask questions like this one. The word organic in chemistry does not mean the same thing it means in a grocery store. It simply means carbon-containing molecules. Molecules built around carbon atoms, which have a particular talent for forming long, flexible chains and rings and lattices, the kind of architecture that makes proteins possible, that makes DNA possible, that makes the enormous variety of living chemistry possible. Carbon is the connective tissue of life as we know it, the scaffolding, and the molecules found in the Enceladus plume were large by molecular standards. Not the small, simple compounds you might expect to find drifting in space, but heavier, more complex structures, the kind that suggested the ocean below was not chemically simple but was, in fact, doing something interesting. Where do complex organics come from? On Earth, they come from living things, or from the chemistry that life runs on, or from the geological and chemical processes that can, under the right conditions, produce them without any biology at all. Which of these was happening in the ocean of Enceladus? The 2018 findings could not say. They were not evidence of life, they were evidence of chemistry. Rich, intricate, carbon-built chemistry happening in liquid water, in the dark. And that is a remarkable thing. It is remarkable because complexity is not nothing. Simple chemistry in a sea is one thing. Complex organic molecules in a sea, alongside hydrothermal activity, alongside molecular hydrogen, alongside salt, that is a different thing. That is a sea that is doing a great deal, a sea that is, by every chemical measure we have, more interesting than most seas we can imagine. The plume, in other words, was not just water. It was a message, and the message, read carefully, said, "There is something happening down here, something chemical, something rich. We do not know exactly what, but it is not nothing." And then, 5 years later, the message deepened. In 2023, the same team, Frank Postberg and colleagues, still working through the immense archive of Cassini data, published again in Nature. And this time, what they had found was phosphorus. Phosphorus. One of the 6 elements considered essential to life as we know it on Earth. The 6 that biologists sometimes group together with the mnemonic CHANOPS: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. You need all 6, more or less, to build a living cell. And phosphorus, of that 6, is in some ways the most important and also the hardest to find. It is the backbone of DNA. Without it, you cannot have a double helix, cannot store genetic information, cannot pass instructions from one generation to the next. It is also the key component of ATP, adenosine triphosphate, the molecule that every living cell on Earth uses to transfer energy, the universal biological currency, the thing that powers every contraction of every muscle you have ever moved. It is in your bones, it is in your teeth, it is in every membrane of every cell in your body. You are, in part, made of phosphorus, and without it there would be no you. It is also, of all of the Knops elements, the one that was most conspicuously missing from the Enceladus story. Carbon, hydrogen, nitrogen, oxygen, now those had all been detected. Sulfur was implied by the chemistry, but phosphorus had not yet been found, and some scientists had wondered whether the ocean might be phosphorus poor, whether this might be a limiting factor, a gap in the otherwise remarkable chemical inventory. And then, in the 2023 data, it was there. Phosphorus, in the form of phosphates, the chemically bonded form in which living things use and cycle it, detected in the ice grains from the plume coming from the ocean. The first time phosphorus had been found in an ocean beyond Earth. The first time the Knops checklist had been completed in any extraterrestrial ocean, all 6 boxes ticked, all 6 essential elements present and accounted for. It was a quiet moment in the story, in the sense that science is usually quiet, a paper published, data reviewed, conclusions stated carefully, no fanfare, no announcement of life found, nothing so dramatic as that. The scientists were meticulous to say what they had found, the ingredients, the chemistry, the presence of the elements, not life itself, not a cell, not a microbe, not a signal of biology, just the building blocks assembled together in a single place in the outer solar system, waiting. The honest and most accurate way to say it is this: Enceladus now has, as far as we can tell, everything that life needs. Liquid water, a source of chemical energy from the hydrothermal vents, carbon, hydrogen, nitrogen, oxygen, phosphorus, and the remaining chemistry to build from. A stable environment, sealed under ice, protected from radiation, kept warm from inside. Everything on the checklist is present. That does not mean life is there. Life requires not just ingredients, but the right sequence of events, the right conditions over the right time scales, the right chemistry happening in the right order. And we do not know if any of that has occurred on Enceladus. It may have, it may not. The ocean is old, possibly very old. It has had time, but time and ingredients are necessary, not sufficient. What we can say, and what is true, and what is quietly extraordinary, is that of all the places we know in the solar system beyond Earth, Enceladus is one of a very small number where the checklist is complete, where every basic requirement for life has been detected, where the ocean is not hypothetical but confirmed, not sterile by chemistry but chemically rich, not disconnected from energy but actively heated, not simple but complex in its organic inventory.
It is a candidate, a genuine one, not a certainty, not even a probability. Cannot put a number on it with any honesty, but a candidate in the truest sense, a place where the question, could life exist here, cannot be dismissed. Cannot be answered with, no, of course not, look at the chemistry. The chemistry says instead, maybe, possibly, we do not know. And that not knowing is not a disappointment. That not knowing is a gift.
Because it means the universe is still holding something back. Still has a question it has not answered for us yet. Still has, somewhere in the dark around Saturn, on a moon small enough to nestle in Arizona, a warm, hidden ocean that may or may not hold something that by any definition we have would be alive. We are allowed to wonder about that. We are allowed to carry it gently, as a possibility, as a soft, open door. We are not required to resolve it tonight. Nobody knows the answer. It is enough to know the question, and to know that it is real, and to drift off with it resting somewhere in the mind like a light left on in a distant room. There, and warm, and not requiring anything of you right now. Let it be there. Let the ocean be there, sealed under its ice, running its chemistry in the dark. And now, for a little while, let's leave the chemistry and come back to the moon itself. To the smaller and simpler, and in their own way, equally beautiful facts. The ones that ask nothing at all of your thinking, that just paint a picture, quietly, one detail at a time. Here is one. A day on Enceladus lasts about 32.9 hours. Not quite a day and a half by Earth's measure, a little more than 32 hours and a little less than 33. So the Sun, or what passes for it at that distance, a small, fierce point of light much dimmer than we know it, would rise and set and rise again in a rhythm just slightly slower than the one you are used to. A longer night, a longer day. Everything stretched gently, the clock of the world running just a little softer. And like our own moon, Enceladus is tidally locked to Saturn. It keeps the same face toward the planet always, turning once for every orbit, so that from any fixed point on its surface, Saturn hangs in the same position in the sky and never moves. Saturn is simply there, enormous, ringed perpetually overhead, or perpetually at the horizon, depending on where you stand. A planet so large that from Enceladus it would appear far bigger than our moon appears to us. A dominant presence in the sky that never rises or sets, but simply inhabits its place, always. On the Saturn-facing side of the moon, you would have Saturn always. On the far side, you would never see it at all. The moon is split into its two permanent faces the way ours is, and the planet rules the sky of one hemisphere the way nothing in our own sky ever does. It is a strange kind of sky to imagine, enormously still in some ways, even as the surface below vents and breathes. And about that surface, the gravity on Enceladus is extraordinary in its gentleness, or rather, in its almost total absence by the standards you are accustomed to. On Earth, if you weigh 70 kilograms, you are held to the ground with a pull that requires effort to overcome, that keeps you from jumping more than a meter or so, that makes carrying things feel like work. On Enceladus, that same person would weigh under 1 kilogram. The surface gravity is roughly 1% of Earth's. A whisper of pull, a suggestion rather than a force. You would be held down technically, but only just. What that would feel like is almost impossible to properly imagine. Walking would not feel like walking. It would feel like drifting, almost. Each footstep would carry you upward, and you would float, slowly, back down. A jump that on Earth would take you half a meter off the ground would, on Enceladus, carry you up by dozens of meters, and you would hang there for a long time, the ice world spread below you, Saturn in the sky if you were on the right hemisphere, the stars overhead if you were not, and you would come back down slowly, very slowly, in the moon's mild and patient grip. The ice grains from the plume behave the same way. They leave the vents at hundreds of meters per second, which on Earth would be nothing, just a spray of water, no different from a garden hose. But on Enceladus, that speed is enough to outrun the gravity entirely. The moon simply cannot hold them. They rise, they drift, they escape, and they become a ring. It is a kind of physics that is easy to know intellectually and hard to feel. That a moon's gravity could be so gentle that its own breath escapes it, that water leaving a crack in the ice just keeps going and becomes part of the architecture of a planet's ring system. But it is true, it is what happens. It is. The gentleness of Enceladus's gravity is part of why it is what it is. A moon that cannot hold its own exhalations, that spills itself softly into space, and in doing so paints a band of light around Saturn. Now, the surface itself. If you looked at the north and south poles of Enceladus side by side, you would see two completely different worlds. The north is old, cratered, pocked, and beaten by the long history of impacts that have shaped everything in the solar system, the relentless slow rain of debris that leaves its mark on every world that does not somehow renew itself. The North Polar region of Enceladus is, geologically speaking, ancient. It has been there a long time, and it shows. The craters accumulate like wrinkles, each one a record of a collision, a small disaster in deep time that left its signature in the ice and then was preserved because nothing came along to smooth it away. The South is young. The South Polar region is remarkably smooth, remarkably fresh, geologically speaking, nearly new. The surface there has been repaved, the ice has been renewed, resurfaced, covered over by fresh material from within. The craters that should be there, by the statistics of impact history, are largely gone, erased by the very activity that makes Enceladus what it is. The warm cracks, the tiger stripes, the plumes, the heat from inside, all of it has been working on that southern surface, reworking it, keeping it young. It is, in a sense, a moon that is actively repairing itself at one end while preserving its age at the other. A moon with a young face and an old face, a south that is still becoming, and a north that has already been. The difference between the two hemispheres is itself a fact, not because it tells us something alarming, but because it tells us something true about what is happening inside. A dead world does not renew its surface. A dead world simply cradles its scars. Enceladus, at least in the south, is not dead. It is, quietly, still in the process of being. And it has been this way for some time. How long exactly is one of the questions that science is still working through. The age of the ocean, the age of the activity, whether it has been continuous or intermittent, whether it might last long into the future. These are open questions, genuinely open, and we will not try to close them here because honesty is more restful than false certainty. What we can say is that right now, as best we can tell, Enceladus is active, its south pole is warm, its plumes are running, and its ocean is liquid. Whatever the past held, the present is ongoing. Now, before we drift toward the close, it seems right to go back to the very beginning, not just of this video, but of the story of Enceladus itself. Back to a time before anyone knew it was anything more than a point of light. The year is 1789. William Herschel is in England, and he has built a telescope. Not just any telescope, the largest telescope in the world at that moment, a 40-foot instrument of considerable ambition, requiring a team to operate and producing views of the sky that nobody had ever had before. Herschel had already discovered Uranus 8 years earlier in 1781 and had continued pushing outward, looking at Saturn's moons, adding to the catalogue of known worlds. On the 28th of August 1789, he turned his great telescope towards Saturn and found two new moons, Enceladus and Mimas, in the same night. Enceladus was a point of light, nothing more. A tiny moving dot distinguishable from the stars only by the fact that it moved, that it tracked around Saturn in an orbit, that it was not fixed. Herschel had no idea what it was. He could not have imagined the ocean or the plumes or the tiger stripes. He could not have known about the hydrothermal vents or the phosphorus or the organic molecules. He saw a point of light, recorded it, noted its orbital period, and moved on to the next observation, the way scientists do. The naming came later. It was William Herschel's son, John Herschel, himself an astronomer of considerable achievement, who established the convention of naming Saturn's moons after the giants and titans of Greek mythology. The giant for whom this moon was named was Enceladus, one of the monstrous children of Gaia and Uranus, the primordial beings who fought the Olympian gods in the war, known as the Gigantomachy. And in the Greek myth, Enceladus was defeated and buried, pinned beneath the earth or beneath the volcano, the legend varying slightly with the telling. beneath Mount Etna. That is the most common version. The giant Enceladus, still restless, still alive despite being buried, breathing and shifting and causing the volcano above him to rumble and smoke. His unease is the volcano's unease. His exhalations are its exhalations. He breathes, and the mountain breathes for him. It is a myth, and we hold it gently as such. A story, not a fact. But there is something in it, some quiet resonance, with a moon that vents from its cracks, that breathes from its south pole, that sends its exhalations upward through the ice and into space. A giant buried in its way beneath the surface, the warmth and the chemistry of it escaping through fractures in the frozen shell. The name was not chosen with any knowledge of the moon's true nature. How could it have been? It was given decades before anyone understood that this moon was doing anything at all. And yet the name fits in that accidental way that sometimes happens when stories and science are both reaching, in their different ways, toward the same underlying truth about the world. Long before any of this was known, before Cassini, before Voyager, there were two spacecraft that passed by Saturn and took a look. Voyager 1 flew past in November 1980. Voyager 2 followed in August 1981. Both sent back images of Enceladus, fuzzy by modern standards as all early planetary imaging was, and what they showed was interesting but not fully understood. The surface was bright, unusually, strikingly bright. Smooth in some places, which was strange. The albedo, the reflectivity, there was high. Something was keeping the surface fresh and white. But what exactly and why and how? That was unclear. The resolution wasn't there, the instrumentation wasn't there, and the pictures were suggestive, but not conclusive. Enceladus was filed in the minds of planetary scientists as a moon worth a closer look. A closer look took 23 years. Cassini arrived at Saturn in July 2004, carrying 13 scientific instruments and the accumulated hopes of a generation of planetary scientists who had been waiting since Voyager for the chance to go back. It was a joint mission of NASA and the European Space Agency and the Italian Space Agency, an international project of considerable scale and considerable ambition. And in 2005, during early orbital passes, something happened that had not been anticipated. The magnetometer, one of Cassini's 13 instruments designed to map Saturn's magnetic field, noticed something wrong with its readings near Enceladus. The magnetic field was bending, not dramatically, not catastrophically, but noticeably, in the way it would bend if there were gas or plasma near the moon, something interacting with the field that shouldn't be there. The moon was too small, too quiet, too apparently inert to be doing that. The finding was published by Michelle Doherty and colleagues in the journal Science in 2006. The conclusion was that Enceladus must be somehow outgassing, releasing material into space, perturbing the environment around it. The magnetometer had detected the plumes before anyone had seen them by noticing the signature their presence left on the invisible field threading through space. This prompted closer looks. The cameras were redirected. The other instruments were turned toward the South Pole. And there they were, the jets, faint at first, at the limit of the imaging, then clearer, then unmistakable, plumes rising from the southern fractures, backlit against the darkness, visible as the spacecraft looked back toward the sun. A magnetic field bending where it should not had led to the discovery of water geysers on an ice moon of Saturn. Science, sometimes, finds things sideways. The answer arrives through a question nobody was asking. Cassini spent years returning to Enceladus, refining its understanding, building the picture fact by fact. 19 flybys in total at various distances and angles, the closest of them in October 2015, the E21 flyby, dropping to within 49 kilometres of the surface, and passing directly through the densest part of the plume, close enough, by spacecraft standards, to be bathed in it, instruments drinking in the spray, sampling an ocean that had never been directly touched. The full accounting of those 19 flybys is still being worked through. The data Cassini collected was vast. It came home as radio signals translated into numbers, translated into science, and the papers emerging from it have continued to appear years after the spacecraft itself is gone. The 2018 organic molecule paper, the 2023 phosphorus paper, others still in preparation, still in review. The conversation Cassini started still ongoing in the journals and the conference rooms of planetary science. It is worth saying quietly that Cassini is gone now. In September 2017, the mission controllers sent it on its final trajectory. They could not risk the spacecraft running out of fuel and drifting, uncontrolled, to contaminate one of the moons it had spent 13 years studying. Enceladus, in particular, a moon with a confirmed subsurface ocean, a candidate for life, could not be allowed to receive an Earth spacecraft carrying Earth microbes and Earth contamination. So Cassini was guided into Saturn itself, sent on a long spiraling path inward that ended in the planet's upper atmosphere, where it burned and was gone. A machine that had been built by human hands, launched from Earth, travelled for 7 years across the solar system, spent 13 years in orbit around Saturn, and discovered more about the 6th planet and its moons than all previous observations combined. The machine ended its existence becoming part of Saturn, becoming, in its small way, part of the planet it had studied. There is something in that which is very quiet and very final and not unhappy. And now, what comes next? The mission is gone, but the question is not. The question of Enceladus, whether that warm, dark ocean contains anything that by any definition is alive, is one of the most important questions in planetary science, possibly in science full stop, because the answer one way or the other changes everything we think about life in the universe. If life is found there, does even microbial life, even the simplest possible biology, it means life is not a singular accident that happened once on Earth and nowhere else. It means life arises when the conditions are right. It means the universe is, in some sense, inclined toward the living. It means that in a galaxy of 100 billion stars, many of them with planets and moons and oceans, the presence of life is not an outlier, but a pattern. If life is not found there, if the ocean is rich and warm and chemically complete and yet empty, if the ingredients are all present and yet nothing has assembled itself from them, that is also a profound answer. It means the step from chemistry to biology is not inevitable, not easy, not something that happens whenever the conditions permit. It means life, even on Earth, was in some sense against the odds. Either answer reshapes everything, and we do not have it yet. Future missions are being studied. The Enceladus Orbilander, a proposed NASA concept, would do what Cassini did, but with instruments specifically designed to look for life. It would orbit the Moon, fly through the plume repeatedly, and sample the spray with the finest analytical tools we could give it. It would, if it flew, represent the most direct search for extraterrestrial life ever conducted, at a place where the ocean comes up to meet the spacecraft, where there is no need to drill through ice or send a submarine into the dark, where the Moon itself does the work, lifting its interior into space, offering it. That mission has not been approved. It may be approved, it may be years away, or decades. Space missions move slowly, funded carefully, developed cautiously. But the concept exists, the engineers have sketched it, the scientists have proposed it. The question has been asked formally enough to start the process. Enceladus will be returned to. In what form and when, we cannot say tonight. But the story is not finished. The chapters ahead are unwritten, and the universe, in its patient way, is not going anywhere. And so, let's come back to the beginning, or nearly. Let's come back to the moon itself. Small and white and impossibly busy for something so quiet-looking. And simply rest here for a moment, in what it is, 500 kilometres across. A world you could hide inside a single American state, tucked beneath Arizona's sun and swallowed whole. A sphere of ice reflecting 90% of the light that touches it, mirror bright, the most reflective solid body we know in the solar system. The kind of brightness that would be beautiful if you could see it, a clean and blazing white in the darkness beyond Jupiter. At its south pole, 4 long fractures, Alexandria, Cairo, Baghdad, Damascus, breathing water into the sky. Hundreds of kilograms per second, rising, drifting, escaping, becoming a ring that surrounds Saturn, a ring that this small moon has been building, probably for longer than there have been human beings on Earth, possibly for longer than there have been mountains on Earth, certainly for longer than anything in human history can reach or remember. Beneath the ice, a sea. A whole salty sea global, sealed in the dark, warmed from below by hydrothermal vents, warmed from within by the patient squeeze of Saturn's gravity and the steady rhythm of the moon, Dione pulling on it in its 2-to-1 orbital dance. A sea with phosphorus in it, a sea with complex organic molecules rising from it, a sea with molecular hydrogen suggesting chemistry at its floor that on Earth sustains entire ecosystems in the absence of any sunlight at all. A sea that may be home to nothing, or a sea that may be home to something. And we don't know. And that's all right. There is a kind of rest available in not knowing, not the frustrated not knowing of a question you need answered before you can sleep, but the peaceful not knowing of a universe that is larger than any one answer, that holds more questions than any lifetime can resolve, that keeps, somewhere in its dark and quiet outer reaches, small bright moons doing extraordinary things in the absence of any observer, running their chemistry in the dark, venting their oceans into space, feeding their rings, keeping their secrets. Enceladus has been doing this for a very long time. It was doing this before Voyager saw it. It was doing this before Cassini arrived. It was doing this before William Herschel found it in his great telescope on an August night in 1789. It was doing this before any human eye had ever turned toward Saturn, before Saturn had a name, before anyone on Earth had worked out that the lights in the sky were other worlds. A small moon breathing quietly in a solar system that had not yet found anyone to notice. And now we have noticed. And what we have found in noticing is more beautiful than anything we might have invented. Wherever you are tonight, whatever corner of the world has you, whatever the hour is, whether a lamp is still on beside you or the room is already dark, this small moon is up there, not close, not reachable. 1.5 billion kilometres, give or take, of empty space between you and its ice. But it is there, orbiting Saturn, running its fountain, keeping its ocean, doing what it does in the same patient way it always has. You are made, in some real sense, of the same elements it carries. The phosphorus in your bones, the carbon in your cells, the water in your blood. These things were made in stars, scattered through space, gathered into planets and moons, and the chemistry of living things by processes that are still running, still ongoing, still producing new worlds and new possibilities in the vast dark beyond the edge of everything we can easily imagine. You are of it, not separate from it. Not an observer looking at a distant thing, but part of the same story. A story that began with hydrogen and helium and time, and has been getting more complicated and more interesting ever since, and has arrived, among other places, at this. You warm and resting, somewhere on this particular world, at the end of a particular day, with your particular lamp and your particular blanket, and the particular quiet of wherever home is tonight. And out there, Enceladus, small and white and impossibly bright, shooting water into the dark, keeping its ocean warm, waiting, in its patient, timeless, unknowing way, for the next question. At the very beginning of tonight, I asked where you were watching from, and I said we would drift slowly through something true about a small moon of Saturn, a fountain running longer than there have been mountains on Earth. I hope that's what we found together, slowly, without any rush, without any need to grasp every detail, just wandering through it the way you might walk through somewhere beautiful on a quiet evening, not memorizing, just being there. If this slow journey through the ice and the ocean and the chemistry of a moon has helped you towards sleep, or has given you something to carry gently into the dark, a small, bright image to rest with, then it has done what it was meant to do. And if you enjoyed being here, a like or a subscribe means more than you might think. Small creators like me rely on your support to keep these nights going, to keep the lamps on and the stories coming, and every one of them is genuinely felt. Thank you for that. And to those who are already here, already subscribed, already familiar with this voice and this pace, thank you especially. You are why the fountain keeps running.
Tell me where you are tonight. What time is it in your corner of the world? What does your night sound like? I love knowing you're there, somewhere out in the dark, in your particular place, the same sky overhead, even if you can't see Saturn from it, the same universe all the way out to that small bright moon. Sleep well. Good night from up here in orbit. I'll keep watch while you drift.